Hello and welcome to In a Container No One Can Hear You Scream, Next Generation Process Isolation. I am Andy. I love to break stuff and then put it back together again once I know what it is made of. And I'm also very proud to be an official trainer and occasional course author for SANS. Watch out for the upcoming SEC 584, HashiCorp, Docker, O'Reilly, and of course, ControlPlane's detailed and extensive low-level cloud-native security courses. And as you may recognize from the title, this talk contains aliens. I'm a founder at ControlPlane, SecOps for Kubernetes, focusing on regulated industries, including financial services. We espouse continuous infrastructure and security practices with a focus on cloud-native deployments, farm to table, or Git to Kubernetes. And in containers, no one can hear you scream. So, what is this talk about? Well, we love Linux. It is a commonly used and well-tested operating system. Containers are a form of isolation provided by the Linux kernel. However, like all software, it has had exploitable vulnerabilities, and advanced sandboxing and isolation techniques have developed to mitigate the risk of unknown existing or future vulnerabilities. While these techniques may also protect against Kubernetes misconfigurations, robust software and infrastructure delivery pipelines are a less complex way of managing that risk. For high-sensitivity infrastructure, workloads, or data, a new generation of sandboxing technologies has emerged. Sometimes referred to as micro-VMs, these technologies are not so easily categorized as they use multiple isolation mechanisms in addition to virtual machines, including containers, and so the generic term sandboxing is used to cover the entire spectrum. So the value of virtualization is a balance of its performance with security. The Linux kernel is written in C, a language with security bugs that have proven notoriously difficult to entirely eradicate. Virtualization can be thought of as a way to abstract a process as far from the Linux system call interface as possible to reduce the chance of exploitable vulnerabilities, using an assortment of LSMs and kernel modules, containers and capabilities, dedicated software, and hardware-assisted virtualization. Use of a type-safe language for the virtual machine's security, such as Golang or Rust, reduces the likelihood of bugs much more difficult to avoid in software programmed in C. So a brief glossary for this talk. The most important thing in a container is either the asset it contains or the data it has access to, be that PII, financial records, passwords that may be reused in other systems. It may also be the algorithms within, including quant trading algorithms, machine learning models, or an organization's secret source. So an untrusted workload is software that cannot be certified as safe to run. That is, a human has not cryptographically signed it with a GPG or similar trusted thing. Untrusted workloads are commonly run in virtual machines that public cloud providers rent to us, in hosted build and CI/CD infrastructure, and uploads to video and audio transcoding services. Untrusted workloads may also include software with published 0 days or CVEs. If no patch is available and the workload is business critical, isolating it further may decrease the potential impact of the vulnerability if exploited. A container image build can be considered untrusted if its desired contents are unknown, as it may contain malicious code to scan network endpoints, exfiltrate code in the container, or attack the host. Container images and code from unauthenticated external sources may also be considered untrusted for risk-averse organizations. A sensitive workload is one whose data or code is too important to permit unauthorized access to. This may include fraud detection systems, pricing engines, or high-frequency trading algorithms. On a Kubernetes cluster, a single workload or an entire tenant may be considered untrusted. Mitigation with Kubernetes native solutions such as admission control and network policy may be sufficient in some cases, but for advanced isolation from unknown vulnerabilities in the Linux kernel and the runc daemon, sensitive or untrusted workloads may be isolated further with next-generation sandboxing. So, what is wrong with containers? Well, let's define firstly what we mean by containers. We start with the high-level interfaces, the container managers, Kubernetes, Docker, and Podman, which interact with their respective libraries to perform useful container management features, including pushing and pulling container images, managing storage and network interfaces, and finally calling the low-level container runtime. That low-level container runtime is directly responsible for starting and managing containers, interfacing with the kernel, and creating that isolated containerized process. A major difference between a container and a VM is that containers do not use hardware-assisted virtualization and so are more widely compatible. But of course, containers do not really exist. They are merely a user space fiction. However, they are kind of a form of virtualization. So a common perception is that containers are optimized for speed and portability, and virtual machines sacrifice these features for more robust isolation from malicious behavior and a higher fault tolerance. But this perception is not entirely true. Both technologies share a lot of common code pathways in the kernel itself. Containers and virtual machines have evolved like co-orbiting stars, never fully able to escape each other's gravity and spewing matter into their shared ether. Container runtimes are a form of kernel virtualization, and the OCI container image specifications have become the standardized atomic unit of deployment. Next-generation sandboxes combine container and virtualization techniques to reduce workloads' access to the kernel by emulating kernel functionality in user space or the isolated guest environment, so reducing the host's attack surface to the process inside the sandbox. Well-defined interfaces can help to reduce complexity, minimizing the opportunity for untested code paths, and by integrating these sandboxes with Containerd, they are also able to interact with OCI images and with shims, with orchestrators like Kubernetes. So, what is wrong with containers? Containers are not inherently insecure, but for some workloads, they leak the host's abstractions too much. Underlying concerns about a root-owned daemon can be assuaged by running rootless containers in unprivileged user namespace mode, but this introduces another risk. User namespaces have historically been a rich source of vulnerabilities. Linux was originally written with a lot of code assuming that it was being run by root in the host namespace, and some of these assumptions have changed with the introduction of user namespaces, the last kernel namespace to be completed. So the answer to whether it is riskier to run a root-owned daemon or user namespaces isn't entirely clear. There have been more high-profile breakouts from root-owned Docker, but this may be down to adoption and widespread use. Rootless containers, without a root-owned daemon, provide a security boundary when compared to root-owned daemons. When code owned by the host's root user is compromised, it can potentially read and write other users' files, ARP spoof and sniff traffic, or install malware to the firmware or kernel. To avoid this potential exploit chain, see, for example, the proc self-exe breakout, replacing the runc binary from inside the container, and attacking the host from inside the container by responding to Docker copy, rootless containers can be created from within a user namespace, and this is supported in the latest versions of Docker and Podman. User namespaces allow non-root users to pretend to be the host's root user. The root in user namespace user can have a fake UID 0 and permission to create new namespaces, mount, net, etc. Change the container's hostname and bind mount and temper fest file systems. This allows the root in user namespace, which is unprivileged in the host namespace, to create new containers. To achieve this, additional work must be done. Network connections into the host network namespace can only be created by the host's root. So, for rootless containers, an unprivileged slurp for netns, guarded by seccomp in the kernel, is used to create a virtual network device. Unfortunately, mounting remote file systems also becomes difficult when the remote file system, for example, NFS home directories, does not understand the host's user namespace. While Rootless Podman has SE Linux support and dynamic profile support, runc and Docker does not yet support AppArmor, and for both runtimes, CRYU is disabled. Both rootless runtimes require configuration for some networking features. CAP-net bind service is required by the kernel to bind to ports below 1024, which is historically considered a privileged boundary, and ping is not supported for users with high UIDs if the ID is not in proc/sys/net IPv4 ping group range, but this can be changed by the host root user. Host networking is not permitted as it breaks network isolation, and cgroups v2's function, but only when running under systemd. Cgroup v1 is not supported by either rootless implementation. So Docker, Moby, and Podman share much of the same code for rootlessness and have been developed in parallel. They share similar performance and features, although Docker has an established networking model that doesn't support host networking, whereas Podman reuses Kubernetes CNI interface. While rootless containers protect the host from the container, some abstractions may still leak from the host, although they become much less dangerous. For example, proc, host devices, the kernel interface. So, is this exposure to C-based system calls in the Linux kernel from a rootless container runtime bad? Well, the kernel of Linux powers the internet and the world, and has done so for decades, but its lack of memory management leads to the same critical bugs over and over again. And when the kernel, OpenSSL, and other critical software are written in C, we just want to move everything as far away from trusted kernel space as possible. Virtual machine research began in the 1960s to facilitate sharing large, expensive virtual machines between multiple users and processors, using hardware, software, or a combination of the two to achieve isolation for processors, memory, and the resources they require from the physical host machine. The host machine is split into smaller, isolated compute units, traditionally referred to as guests. These guests interact with a virtualized interface to the host's CPU and devices, and the interface intercepts system calls to handle them itself by proxying to the host's kernel or using its own code to handle the request. Full virtualization, for example, VMware, emulates hardware and boots a full kernel inside the guest. Operating system level virtualization, for example, a container, emulates the host's kernel using namespaces, cgroups, capabilities, and seccomp, and so can start a containerized process directly on the host kernel. Processes in containers share many of the kernel pathways and security mechanisms that processes in VMs also execute. To boot a kernel, a guest operating system will require access to a subset of the host machine's functionality, including BIOS routines, devices and peripherals, for example, keyboard, graphical or console access, storage and networking, as well as an interrupt controller and interval timer, some source of entropy for randomization, and the memory address space that it will be run in. It should be noted that despite many decades of effort, in practice, no virtual machine is completely equivalent to its real machine counterpart. Inside each guest virtual machine is an environment in which processes or workloads can run. The virtual machine itself is owned by a privileged parent process that manages its setup and interaction with the host. This is known as a virtual machine monitor, or VMM. This is also previously known as a hypervisor, but the distinction is blurred with more recent approaches, so the original term VMM is preferred. Linux has a built-in virtual machine manager called KVM that allows a host kernel to run virtual machines. Along with QEMU, which emulates physical devices and provides memory management to the guest, and can also run by itself if necessary, an operating system can run fully emulated by the guest OS and QEMU. This emulation narrows the interface between the VM and the host kernel and reduces the amount of kernel code the process inside the VM can reach directly. This provides a greater level of isolation from unknown kernel vulnerabilities. Different technologies take different approaches to moving away from Linux system call interaction for the guest. Linux containers are the most lightweight form of isolation as they allow workloads to use kernel APIs directly, minimizing the layers of abstraction. gVisor starts a KVM virtual machine, or operates in ptrace mode, and inside starts a user space kernel, which proxies system calls down to the hosts using a Sentry process. This trusted process re-implements 237 Linux system calls and only needs 53 system calls to operate itself. It is constrained to that list of system calls by seccomp, and it starts a companion file system interaction process called gopher, which prevents a compromised Sentry process interacting with the host file system. Finally, it also implements its own user space networking stack. Conversely, Firecracker, while also using KVM, instead of implementing the heavyweight QEMU process to emulate devices, as a traditional Linux virtual machine might do, it starts a stripped-down device emulator instead. This reduces the host's attack surface and removes unnecessary code, requiring only 36 system calls for itself to function. gVisor and Firecracker both operate on the premise that they're statically typed, i.e. Golang or Rust, system call proxying in between the process and the host kernel is more secure against untrusted workloads than the Linux kernel itself, and that their performance is not significantly impacted. And finally, at the other end of the spectrum, KVM and QEMU VMs emulate hardware and so provide a guest kernel and full device emulation, which increases startup times and therefore memory footprint. While guest OS virtualization is expensive due to many layers of abstraction, it permits running unmodified guest operating systems and does not require hardware, that is, CPU, virtualization support. gVisor, Firecracker, and Kata Containers all take different approaches to virtual machine isolation and aim to challenge the perception of slow startup time and high memory overhead. Each system is a combination of virtual machine and container technologies, some VMM processes, a Linux kernel within the virtual machine, and, once the kernel has booted, a Linux user space in which to run the process. And some combination of kernel-based isolation, that is, container-style namespaces, cgroups, and seccomp, either within the VM, around the VMM, or some combination thereof. gVisor protects App Engine's standard environment, Google Cloud Functions, Cloud ML Engine, and Google Cloud Run. And as it has been modified for Google GKE, currently has the best integration with Docker and Kubernetes from these sandboxing technologies. It can be considered as either a merged guest kernel and virtual machine monitor, or as seccomp on steroids. As well as using its Sentry process, it also provides a masked view of the proc and dev virtual file systems. These file systems have historically leaked the container abstraction by sharing information from the host, such as memory, devices, processes, etc. Sentry prevents the application interacting directly with the host kernel, and seccomp is used around the gVisor kernel to limit system calls and prevent escalation in case of tenants breaking into Sentry and attacking the host kernel. Implementing a user space kernel is a Herculean undertaking, but the lack of full system call support means some applications are not able to run in gVisor. In practice, most of these system calls were excluded for a reason, and compatibility is generally very good. A side process to the Sentry called gopher handles I/O, e.g. disks, devices, which is historically a common attack vector for VMs. Separating this process provides resistance to compromise. If Sentry has an exploitable bug, it can't be used to attack the host's devices because they are all proxied through Gopher. However, this comes at the cost of some reduced application compatibility and a high per system call overhead. Of course, not all applications make a lot of system calls, so this is dependent upon usage. Sentry's user space OS kernel implements all the kernel functionality needed by the untrusted application. Although it does make some host system calls to support its operation, it will not allow the application to directly control the system calls that it makes to the underlying Linux kernel. Application system calls are redirected to Sentry by a platform syscall switcher that intercepts the application when it tries to make system calls. Sentry sits in a loop, waiting for a system call to be generated by the application. It then captures the system call, handles it, and returns a response to the process. A simple concept that abstracts the complexity from a user. The platform syscall switcher, gVisor's system call interceptor, has two modes, ptrace and kvm. The ptrace system call provides a mechanism for a parent process to observe and modify another process's behavior. Ptrace sysmu forces the traced process to stop an entry to the next syscall, and gVisor is able to respond to it or proxy the request to the host kernel, going via Gopher if I/O is required. Firecracker is a VMM that boots a dedicated virtual machine for its guest using KVM. But instead of using KVM's traditional device emulation pairing with QEMU, Firecracker implements its own memory management and device emulation. It has no BIOS, instead implementing Linux boot protocol, no PCI support, and stripped down simple virtualized devices with a single network interface, a block I/O device, a timer, clock, serial console, and a keyboard device that only simulates Control-Alt-Delete in order to reset the VM. Firecracker itself will be compatible with Kubernetes and OCI when the Firecracker Containerd project is complete. The Firecracker VMM process that starts the guest virtual machine is in turn started by a jailer process. The jailer configures the security configuration of the VMM sandbox, the GID and UID assignment, network namespaces, creating a chroot and C groups, then terminates and passes control to Firecracker, where seccomp is enforced around the KVM guest kernel and the user space that it boots. Where gVisor proxies I/O through a secondary process, Firecracker uses the KVM virt.io drivers, proxying from the guest Firecracker process to the host kernel using the VMM. When the Firecracker VM image starts, it boots into protected mode in the guest kernel, never running in its real mode. Firecracker invokes far less host kernel code than traditional LexC or gVisor once it has started, although they all touch similar amounts of kernel code at runtime. Performance improvements are gained from an isolated memory stack and lazily flushing data to the page cache instead of disk to increase file system performance. Firecracker supports arbitrary Linux binaries, but does not support generic Linux kernels. It was created for AWS's Lambda service, forked from Google's Chrome OS VM, CrossVM. Firecracker is a statically linked Rust binary that doesn't pollute the host file system and is compatible with Kata Containers, Ignite, Firecube, Firecracker Containerd. It provides soft allocation for more aggressive bin packing and a greater resource utilization. Kata containers are lightweight VMs containing a container engine highly optimized for running containers. They are the oldest and most mature of the recent sandboxes and were originally called clear containers. Compatibility is wide, with support for most container orchestrators. Grown from a combination of Intel Clear Containers and hyper.sh run-v, Kata Containers wraps containers with a dedicated KVM virtual machine and device emulation from a pluggable backend, QEMU, QEMU Lite, QEMU, a custom stripped-down QEMU, or Firecracker. It is an OCI runtime and supports Kubernetes, which does not require a modification of container images. The Kata container runtime launches each container on a guest kernel in its own hardware-isolated VM. The Kata runtime is the VMM and interface to the OCI. Kata proxy handles I/O for the Kata agent and therefore the application using KVM's virt.io serial and multiplexes a command channel over the same connection. Kata shim is the interface to the container engine, handling container lifecycles, signals, and logs. The guest is started using KVM and QEMU or Firecracker. The project has forked QEMU twice to experiment with lightweight start times and has re-implemented a number of features back into QEMU, which is now preferred to QEMU, the most recent fork. Inside the VM, QEMU boots an optimized kernel and systemd starts the Kata agent process. Kata agent manages the containers running inside the VM, which uses libcontainer and so shares a lot of code with runc. Networking is provided by integrating with CNI or Docker's CNM, and a network namespace is created for each VM. Because of its networking model, the host network cannot be joined. SE Linux and AppArmor are not currently implemented, and some OCI inconsistencies limit the Docker integration. An honourable mention, many new VMM technologies have some Rust-lang components. So, is Rust any good? It's similar to Golang in that it is memory safe, its memory model, virt.io, etc., but it is built atop a memory ownership model, which avoids whole classes of bugs, including use after free, double free, and dangling pointer issues. It has safe and simple concurrency, and no garbage collector, which may incur some virtualized overhead and latency, instead using build time analysis to find segmentation faults and memory issues. Based upon the safeness of the language, rust-vmm is a fast development toolkit for new VMMs. It is a collection of building blocks, that is, Rust crates, comprised of virtualization components. These are well tested and therefore better secured and provide a simple, clean interface. For example, the VM memory crate is a guest memory abstraction, providing a guest address, memory regions, and, when used in Firecracker, guest shared memory. The project was birthed from Chrome OS's Cross VM, which was forked by Firecracker and subsequently abstracted into the hypervisor from scratch crates. This approach will enable the development of a plug-and-play architecture for hypervisors, which isn't yet prevalent in the industry. So how do we run these things? Well, Kubernetes and Docker support different container runtimes at the same time. A node can run pods with different CRIs. This means that we can separate our workloads. Docker is able to run any OCI-compliant runtime. Kubernetes requires a runtime to also be CRI compliant. While Kubernetes does not yet distinguish between types of sandboxes, we can still set node affinity and toleration so that we schedule our pods onto nodes that have the relevant sandbox technology installed. What are the risks? Well, the degree of access and privilege that a guest process has to host features or virtualized versions of them impacts the attack surface available to an attacker in control of the guest process. So this new tranche of sandbox technologies is under active development. Its code, and like all new code, is at risk of exploitable bugs. This is a fact of software and is infinitely better than no new software at all. Potentially, these sandboxes are not yet a target for attackers. The level of innovation and baseline knowledge to contribute means the barrier to entry is set high. From an administrator's perspective, modifying or debugging applications within the sandbox becomes slightly more difficult, similar to the difference between bare metal and containerized processes. These difficulties are not insurmountable and require administrator familiarization with the underlying runtime. It is still possible to run privileged sandboxes, and although the risks are fewer than privileged containers, users should be aware that reducing isolation increases the risk of running the process inside the sandbox. Narrowing the interface between a sandbox process and the host is a risk-based decision. There are some trade-offs. Debugging becomes much harder, and traditional tracing tools may not have great compatibility. There is a performance impact, but this may be negligible for some workloads, and benchmarking is strongly encouraged. As next-generation runtimes have focused on stripping down legacy compatibility, they are very small and very fast to start up compared to traditional VMs. Not as fast as LexC or Moby, but fast enough for function as a service providers to offer their aggressive scale-up rates. So application workloads should be categorized by risk. Does this application access a high-value asset? Is this application able to receive untrusted traffic? Or have there been vulnerabilities or bugs in this application before? If the answer to any of those is yes, you may want to consider a next-generation sandboxing technology. So, unless you have specific problems, containers are probably just fine. For higher sensitivity workloads and data, perhaps we want more isolation. There is an affinity between some of these technologies and their supporting cloud provider, which makes it a lot easier to use a supported runtime, and rust-vmm means that there will be many more hypervisor-based container runtimes in the future. Thanks for listening. Have a wonderful day.